Imagine building a part for a jet engine, or maybe a custom medical implant, but instead of carving it from a solid block of metal, you're literally growing it, layer by microscopic layer, from a cloud of fine powder. It sounds like science fiction, right? Well, this is the world of metal 3D printing. But this incredible technology has a dirty secret. It can be unbelievably wasteful. Today, we're going to look at a breakthrough that tackles this problem head-on, using invisible forces to make manufacturing smarter and way more efficient.
So, here's our game plan. First, we'll cover the basics of how this technology even works. Then, we're going to zero in on the massive efficiency problem it faces. From there, we'll explore 4 totally different solutions that engineers came up with, see which one was the clear winner, and finally, talk about what this all means for the future of how we make things.
All right, first things first, let's get a handle on the fundamentals. The fancy term for all this is additive manufacturing, and we're about to dive into one of its most powerful forms, the kind that can create solid metal objects straight from a computer file.
You know, most manufacturing that we think of is subtractive. You start with a big block of something, like wood or metal, and you just carve away everything you don't need. Well, additive manufacturing completely flips that on its head. It builds objects from the ground up, one super thin layer at a time. This lets engineers design these incredibly complex internal structures that would be literally impossible to make any other way.
Okay, so a really cool type of AM is called direct metal deposit, or DMD. And the whole process is like a high-tech ballet. It all kicks off with a digital design, a CAD file on a computer. Then, a super powerful laser creates this tiny little molten pool on a metal surface. At the exact same time, a nozzle shoots a stream of fine metal powder right into that pool. The laser moves, tracing a path. The powder melts and fuses, and layer by painstaking layer, a solid metal part just appears out of thin air.
And that brings us to the big problem, this central challenge. DMD is absolutely revolutionary, but it's got this massive hidden cost that's really held it back, especially when you're working with the most advanced and most expensive materials out there.
To really get the problem, think about spray painting something complicated, like a bicycle frame. No matter how careful you are, a ton of that paint just ends up as mist in the air, right? It totally misses the target. Well, the exact same thing happens in direct metal deposition. Not all the powder that gets sprayed actually becomes part of the final object.
Engineers actually have a name for this: powder catchment efficiency, or PCE. It's a really simple but kind of brutal calculation. You just take the weight of the finished part and you divide it by the total weight of all the powder you sprayed. That number, the PCE, is the key thing that tells you if the whole process is even worth it financially, especially when you're talking about exotic metal alloys.
Now get this, a process that's considered significantly good has a PCE of only around 40 to 65%, and that's the best case scenario for standard operations. It's wild.
Yeah, you heard that right. In some cases, more powder is wasted than is actually used to build the part. Now, when you're dealing with materials like high-grade titanium or these nickel superalloys that can cost hundreds of dollars a kilogram, throwing away more than half of it is a huge financial and environmental issue. It's been a major roadblock for this technology.
So, how do you solve a problem that's so fundamental to the process? Well, researchers didn't just try one little fix. They explored 4 totally different ways to assist the process, and each one uses a different kind of invisible force to try and steer that lost powder back to where it belongs.
The first 2 methods use these invisible forces. Ultrasonic assistance is basically like shaking the build plate with incredibly high-frequency sound waves. This helps the molten metal settle more evenly and actually makes the final part stronger. Then you've got magnetic assistance, which uses a powerful magnetic field to literally grab onto certain types of powder particles, like iron or steel, and actively pull them right into the laser's path.
The other 2 ideas are all about controlling the environment. Electrostatic assistance works kind of like when a balloon sticks to a wall because of static electricity. It uses an electric field to make the powder particles sticky so they're drawn to the target area. And vacuum assistance? Well, it just removes all the air from the equation, which gets rid of variables like humidity and oxidation and gives engineers the ultimate control over the whole deposition process.
Okay, so we've got 4 contenders in the ring: sound waves, magnets, electricity, and a vacuum. After running all the tests, did one of these methods actually stand out in the fight against waste? Oh, yeah. The data couldn't have been any clearer.
So the baseline process just on its own was hovering around 45% efficiency. But just look at what happens when you turn on the magnets. On a steel base, the efficiency shot up to 56%, and on a nickel base, it soared all the way to 63%. That is a massive improvement. We're talking a boost of up to 25% over the standard method.
So why were the magnets so effective? And why did the type of metal base matter so much? Well, this quote from the research paper really gets to the heart of it. By using a ferromagnetic substrate, that's just a material that responds strongly to magnets, like steel or nickel, you basically turn the entire build plate into part of the magnetic system. This creates a much stronger, more focused field right where you need it most, and that's what captures all that powder that would have been wasted.
Now, boosting efficiency by a quarter might just sound like a nice little technical improvement, but the ripple effects this has on the future of high-tech manufacturing are absolutely huge. This is about so much more than just saving a little bit of powder.
This single innovation really unlocks potential across the board. First, lower costs make this advanced tech accessible to more industries. That 25% efficiency boost could translate to millions of dollars saved on a single aerospace project. The improved process also leads to stronger, higher quality parts. This opens a door for creating next-gen components, custom medical implants, things that were just too expensive before. And maybe the best part of all, this magnetic assist system can likely be retrofitted onto existing machines, upgrading a whole fleet of technology that's already out there in the field. So what you have to realize is that this research isn't just a small step, it's a leap towards a totally new way of thinking about intelligent manufacturing. We are literally learning how to manipulate matter at a microscopic level using invisible fields of energy. It points to a future where we don't just build things layer by layer, but where we guide every single particle with absolute precision. The age of intelligent matter, it's really just beginning.